8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start.
Come on, baby. Come on, baby.
America's first space shuttle.
Hello, and welcome to Astronomy Toronto. My name is Randy Attwood, and I'm a member of the Royal Astronomical Society of Canada. This show is produced by the Toronto Centre of the Royal Astronomical Society of Canada, where we look at the activities of both amateur and professional astronomers here in the Toronto area, and sometimes look at the space happenings around us. Today is one of those days where, as you can see from the introduction, we're going to be looking at the Space Shuttle. But not only the Space Shuttle, we're going to concentrate on what Canada has to do with the Space Shuttle, especially the remote manipulator system on the shuttle, or the ARM. The launch at the beginning was the first launch of a space shuttle, and was on April 12th with John Young and Robert Crippen in the STS-1 mission, or the Space Transportation System 1 mission. We have some slides of the Space Shuttle that we look at just before we get to talk about the ARM. Maybe some of you aren't totally aware of the Space Shuttle and its uses, so we'll more or less look at a basic Space Shuttle mission like the STS-1 mission we saw last April. So maybe we'll just go to these slides and look at a basic Space Shuttle mission. Here's a general view of the orbiter. This is the reusable part of the spacecraft, which comes back to Earth. In the front you can see where the crew of from 2 to 7 astronauts are. And in the long part is the cargo bay, where all the satellites and payloads are kept. And of course in the back is the engine. And the wings and the tail make it easy for the space shuttle to come back and land like a glider, as we'll see a bit farther along. Of course the engines are used only as it's going up towards orbit, but it's not used when they're coming back to Earth. Here's a picture of what you might remember. The Enterprise was the first space shuttle which was built. It was never built to go into space. It was used to be carried on a 747 and dropped in 1977 for astronauts to practice the landing techniques of gliding this several hundred-ton spaceship back to Earth successfully. 747 is also used to carry the space shuttle back from California back to Cape Canaveral for when they're ready to refurbish and send the space shuttle up again. This is what the space shuttle looks like when it's going to be launched. Of course, you see the orbiter on top, and then there's a big external fuel tank underneath, which holds the liquid oxygen, liquid hydrogen fuel for the 3 engines in the shuttle. And then the 2 crayon-like sticks on the side are the solid rocket boosters, which burn for about 2 minutes during launch and add about 1 millionth pounds of thrust each. And after 2 minutes, they fall off and are picked up by tugs in the ocean. Here we have a picture of, in the early launch phase, of course, you can see the 3 main engines at the bottom burning and the 2 solid rocket boosters. 2 minutes and 12 seconds after launch, the solid rocket boosters fall off, and some of you may remember seeing this on television when this happened. You can see the 2 fall off and they fall back into the ocean. This is what the shuttle looks like in orbit. The first shuttle mission didn't have anything in its cargo bay, but what I want to show here is that long stringy thing in the middle there. That's the ARM. That's what we're going to be talking about today. And we have a guest from Spar Aerospace here today, here in Toronto, where they make and they've designed and made this ARM. So the ARM is used to carry, to deploy, and also retrieve these scientific payloads, space shuttle payloads and satellites in orbit. Of course, you can see the cargo bay doors have to be opened for this. Several satellites can be taken up at once and deployed, and then the space shuttle can bring back old satellites, of course, if they need to be fixed for some reason. Well, after the flight is over, the space shuttle leaves its orbit and comes down re-enters the atmosphere and comes down like an airplane, like somebody coming back from a trip on a DC-9. And in this picture here we see one of the tests of the Enterprise where it landed on a runway, proving that the space shuttle can indeed come back through the atmosphere and land like a glider. Well, our guest today is Mr. Chris Browning from Spar Aerospace, which is here in Toronto. And Spar Aerospace, Chris is the public relations officer for Spar, I might say, and which is responsible, of course, for designing and building the arm. Chris, thanks very much for coming by today.
Oh, thank you. I'm glad to be here.
Before we talk about the space shuttle and its arm, Chris, could you tell us a bit about Spar itself?
Sure. Spar Aerospace Limited is, we think, Canada's largest space engineering company, as well as being involved in other areas of aviation, such as manufacturing aircraft gearboxes, repair and overhaul to aircraft. We are involved in building satellites, complete satellites for Canada, and subsystems for satellites, not only for this country, but many other countries in the world. And of course, as you mentioned, we're the prime contractor for the remote manipulator system, Canada's contribution to the space shuttle.
Well, you mentioned satellites. Has Spar had any involvement with Canadian satellites before the space shuttle?
Oh yes, we've been in the business of space engineering since 1968 when the company was founded. And Spar has been involved in every Canadian satellite put into orbit to date, which, by the way, is 9 satellites, something that perhaps Canadians aren't aware of.
Well, let's take a look at some of those satellites. I think
Okay.
we have some slides of them. We'll be able to go to some pictures of these Canadian satellites. Here's a bit of a promo for Spar, I guess, but it's a very nice picture, so we thought we'd throw it in. The first satellite is Alouette 1.
Right, this is Canada's first satellite, and it put us in the space business, I guess. Alouette 1 was made Canada the third country in the world to have a satellite in orbit. Alouette 1 was built completely here in Canada.
And it was launched back in 1962.
That's right, by the Americans, of course.
That's right. So they used a rocket to send that up. We didn't have a rocket to send that up ourselves.
That's right. The Americans supplied launch facilities for all Canada satellites.
Here's another satellite.
Yes, this is one of the ISIS satellites. This was the third one, ISIS 1, and it again, as was Alouette, was a research satellite.
What did it study?
The upper atmosphere, the ionosphere, basically studying it from the other side. There was a lot of research from the ground, and this was from space. This is Anik A, Canada's first communication satellite. In fact, it was the world's first communication geosynchronous satellite, which has become the world standard for communication satellites now.
An interesting point is Anik is Inuvik, which means brother in English.
Yes, yes.
Which is, I think, an appropriate name. Now, they put this up in geosynchronous orbit.
Right. Geosynchronous orbit means it sits out in space at one point over the Earth's surface, of course, in this case, over Canada.
Right.
And it acts as a relay station. Here, this slide shows the complete network. The lights on the map of Canada are the Earth stations, and we have the 3 Anik A's in orbit, and the Anik A's act as relay stations between the ground stations to transmit TV, radio, and other forms of communication.
Of course, they're not that close together. They might be thousands and thousands of miles apart.
Well, they're fairly close, but they're not that close to the Earth's surface. They're over 22,000 miles away. This is just a schematic drawing, I suppose, more than anything else.
Right. So I think they were the ones that sent TV all the way to the north, isn't that right?
That's correct. That's one of the reasons that Canada is being so interested in satellites.
Right.
Here we see another Canadian satellite, Anik B. This is the Hermes satellite, an experimental satellite under construction at Spar. You can see the gold that you can see are the solar blankets.
Oh, so we see them coming out the solar panels.
Right. Here in orbit, we see the solar panels on either side of those wings. These are the solar panels that gather sunlight to power the various electronics on board the satellite.
And Spar had built those, is that right?
Yes, we built the solar arrays and many other components, actually, for the satellite.
Well, here's Anik C, which is a new Anik satellite, but it isn't up yet.
Right. Spar is working on it at the moment. This is the next generation of Canadian communication satellites.
And this will be launched from the shuttle, is that right?
That's correct, yes. The first Canadian satellite to be shuttle launched. Here we see the deployment of an Anik C type of satellite from the shuttle. The shuttle orbits in low Earth orbit around 100 miles, and then a rocket engine on the satellite itself boosts it up to geosynchronous orbit, which, as I said, was slightly over 22,000 miles away from the Earth's surface.
Interesting point is the shuttle can only bring it up to 150 miles. It needs a rocket of its own to go the remaining distance, doesn't it?
That's right. There's some satellites used for remote sensing, weather forecasting that are in low Earth orbit. But geosynchronous satellite, you have to sit that far out in space to allow it to sit in one point over the Earth's surface.
Well, let's talk about the arm now. We have a model of the space shuttle here, Chris, so if you'll let me be your co-pilot, we can
Sure.
see how the arm works.
Okay.
Once they get up into orbit, this is what it looks like up in orbit.
Right, right. And then the cargo bay doors open,
Right.
and inside we have whatever cargo the shuttle might be carrying into space.
Right.
A satellite or a scientific payload. In this case, we have the European Space Agency's Space Lab.
Right. Well, here we have the arm. It's attached right here. We'll just
Right,
attach it like it would be used.
And it would be in a rest position inside, and then it would, once the cargo bay doors open, it would be moved out,
Right.
and then say you were deploying a satellite, it would be moved down to hook up to a satellite, take it out of the cargo bay door, release it, and then the shuttle would go down to Earth, leaving the satellite in Earth orbit.
And where would the people operating this be?
Well, the people, all the astronauts would be in the shuttle cabin
Right.
that you're pointing at there now, and a payload specialist would work at the rear location, looking out windows in the back of the cabin, and also using TV cameras to observe the motion of the arm and the payload.
Oh, very good. That's a good representation. Tell me, how did Canada get involved with the space shuttle in the first place?
Well, in the early 70s, Canada decided that it would be beneficial, or rather, our government decided it would be beneficial to become involved in the shuttle program so that we could develop a space industry. Of course, space industry means jobs, it means export dollars. So Spar Aerospace was given a contract to build the remote manipulator system, or ARM, for the shuttle for NASA.
Very good. Well, we have some pictures of the arm itself, and maybe we'll give have some artist views of what the arm looks like. Then look at the actual arm, which is, I think, on the way down to Cape Canaveral at this moment, or it should be down there by now.
That's right.
And I think it's going to be used for the first time on the next Columbia mission, which should be in the fall sometime. So we have some slides of the arm and how it looks on the space shuttle.
Well, here we have the arm deployed in space. This slide emphasizes the end effector, which is a grappling fixture that links on to satellites, payloads, and in this case it might be grabbing one that's already in orbit to move it back into the payload bay to bring it back to Earth for servicing, whatever.
The interesting thing, Chris, is though it so much resembles a human arm.
Yes, I'm glad you pointed that out. In point of fact, the remote manipulator system is an anthropomorphic arm, and it has a shoulder joint, an elbow joint, and wrist joints. And in point of fact, it serves exactly the same purpose as the human arm. It's used as a device to, in whatever way, handle things in space.
But unlike a human arm, it has a lot more freedom of movement, doesn't it? It can bend a lot more than just an elbow or shoulder can, as we can see by that diagram.
That's basically correct, yes. It has a wide degree of motion. It can maneuver almost anywhere in the area off the shuttle.
Well, here we are at Spar, right?
Right. This is in a Spar clean room. The arm is under development here. It's mounted on a test fixture which simulates zero gravity, at least in the horizontal plane. Here we have another shot of the same setup. If you can see in the background, you see a technician operating the arm.
The interesting thing also is that it can't support its own weight on Earth.
That's right. In space, it can handle the full payload capacity of the shuttle, 65,000 pounds. On Earth, because of gravity, it can't even lift its own weight.
Okay, there's a technician with the grappling fixture now.
Right. If you can imagine the technician as a satellite, that's how the arm would link onto the satellite and maneuver it around, and then release it when the movement was completed.
So if a satellite doesn't have that fixture, it can't be picked up.
Right, and here we see the space telescope, which is under construction, and the grapple fixture, as we call it, is installed about 3/4 of the way up the space telescope, and that's how the arm links on to a payload.
So it can be taken out, but it'll also be brought back, and I think that's what they intend to do with the space telescope.
That's right, that's right.
To bring it back in after it's been used for a few years.
Yeah.
Do you know when the Space Telescope is to be launched?
I'm not exactly sure. It's in the mid-'80s, but it's under construction now. Here we see the Space Telescope actually being deployed from the shuttle, and you can see the arm in motion there.
I think there might be an astronaut with the arm too. I think the Space Telescope has to be serviced before it is deployed, and then in a few years
Right.
it'll be brought back.
That's another application, in fact, of the arm, extravehicular activities, or EVAs, as we call them. A platform, for example, can be affixed to the arm.
Well, the Space Telescope is going to be a revolutionary advancement in astronomy because if you have a telescope above all of the atmosphere, you're above all the pollution and all the air, and this Space Telescope is going to be 7 times better than our best telescopes here on Earth. So all the astronomers are anxiously waiting for the first pictures back from that Space Telescope, and of course the pictures will be sent back via television, and we'll be able to see farther into space, and of course as you look farther into space, you're looking back in time, and we might even get a chance to look back at the beginnings of our universe.
Yes. People sometimes ask the usefulness of all this, and you've just described a very useful application.
I agree. It's going to be a super thing to have. The arm looks complicated. I mean, maybe we could talk about now of how the simulator that Spar has, which
Yes.
gives astronauts a chance to practice on Earth how the arm will react in space.
Okay.
There is a simulator at Spar, is that right?
That's right. We call it SimFac, and the simulator, as you say, allows astronauts to actually practice the fairly complex controls that are needed to operate this thing. And point of fact, we've trained over a dozen astronauts in the last year or so on our simulator.
Well, we have some slides of the SimFac up and down for you, so maybe we can go to those now and see what the simulator looks like. This is a view in the future, looking out the back of the shuttle when it's in orbit.
Yes, here we have 2 astronauts, payload specialists as they call them, operating the various controls for the arm. Through the window we can see the payload bay, and beyond that a large space structure. This is for the future. It's speculation at this point, but I think it will probably occur.
Right. Well, of course, SimFac is short for Simulation Facility, which, as you've mentioned, the astronauts have come up to use. It's the only
That's
way
right.
they can see what the arm looks, how it acts in orbit.
That's right. Our SimFac is a NASA training facility, and in fact it's the only one for the remote manipulator system. So we train all astronauts who will be using the RMS.
Well, it doesn't look like much from the outside, but Chris and I have been inside, and it's really something.
Yes, it's a matter of fact a complete simulation of the inside of the cabin of the space shuttle, and of course it's backed up by a full room of computers. Here we see someone actually operating the controls with simulated views on the various screens.
So, as he moves the hand controllers, what does he see out his windows?
Well, in real life, in space, he'd be seeing, either by a television view or actually out the port, a view of the shuttle, of the RMS, the arm moving a payload. Here, we have a simulation of that, and the payload would be a large satellite, what have you. And you can see the arm there on the left, connecting it to the space shuttle.
So as he moves his hand controllers, it tells the computer that, hey, I want to move the arm this way, that way, and the computer does that, doesn't it?
That's right. Basically, the computer does the same thing as your mind does. If you decide to, say, touch your nose with your finger, you don't figure out each joint movement. Your mind does it subconsciously. Here's another view of the...
Well, this is the observer station, I think.
Yes, right. It's showing the same views, but this is the observer station outside the simulator, where various problems perhaps are fed in to give the astronaut a hard time trying to solve emergencies that might occur.
I see. It's interesting that all the astronauts that have been there, all their movements is kept on tape and then analyzed afterwards.
That's right, yes. I think one thing that NASA wants to do is judge how well the various astronauts can operate these things before selecting payload specialists.
I see. That's really something. The fact that as you move it, the computer immediately draws what you've done and sends it back to the TV screen immediately. So
Yes.
you react, and then they might feed you problems, and oh, who's this? Someone we know?
Yes, this is myself just taking a look at the SimFac. I seem to be having a good time.
Yes, it was a really interesting experience to go there and see how it worked.
Yes. Yes.
Well, as we've said before, the arm hasn't been in the shuttle on a flight. The first flight didn't carry it. The second one will. And then on all subsequent shuttle flights, the arm will be up. What is the future for the arm, Chris? I mean, you've got each shuttle having an arm, and it'll be used to deploy satellites. But what are we looking at, say, 5, 10 years down the road with the arm?
Well, it'll be used, I think, as you say, in almost every shuttle mission. There's many other applications that it could be used in the future. For one thing, space construction, which is now seeming with the shuttle. Space construction is a very good possibility, and our arm could be used to, say, assemble girders to create a large space platform for whatever purpose. Solar power satellites is one thing that's talked about at the present time. So we hope that there'll be a large market for it in the future, in space.
Well, we have some slides of maybe some future concepts, some ideas, but maybe ideas that will turn into reality. So let's take a look at those slides now and see what's in store for our arm. Through the 80s.
Yes, it might be the 90s or even the turn of the century before some of these things actually happen. But here we have, as I say, one of these large space platforms which our arm could be used to assemble. In fact, I think we see the space shuttle here with the arm maneuvering one of these girders.
That's right, and a lot of this structure, of course, will be built up in space itself. They have a beam builder that will be carried in the shuttle.
That's right. That's one of the methods being explored now, yes. Here's a construction concept, an artist's impression of how our arm could be mounted on basically a space crane. Here it isn't actually on the shuttle, but on the construction site itself, maneuvering beams, assembling beams, what have you. Here's another view of a different type of large structure. This one, I believe, would be a manned structure, and you see the shuttle deploying components or building blocks from the cargo bay and putting them in place in the structure.
So how many years off is this? Does anyone really know?
Well, I'd certainly say 20 years.
Mm-hmm.
We're researching it now. Here's a terrestrial application that we might see in the very near future, using the arm and an undersea robot to fix cables, undersea gas lines, for example.
So would there be someone down there with that arm, or would they be up, say, above operating
There could
it?
be. This particular one was a complete robot. It would be controlled from remote. This is a possibility, a study that Spar undertook for a disabled person in a wheelchair. He could use one of our arms to act as his own arm with, you see, his right hand operating the controls to do almost anything a human arm can do.
I remember when we were at Spar, there were
Yes.
several arms under development which were going to be used by Ontario Hydro to be used at their nuclear reactor plants.
That's right. This is something that we're very much hoping will be occurring in the near future. We're in our second study contract for Ontario Hydro, and basically it would be a robot arm. It would be used to reduce human exposure to radiation within the nuclear reactor itself, and to do repair work, emergency work, what have you. The sort of thing that if they'd had it at some of the emergencies in the past might have been very helpful.
It's very exciting. It's certainly something to be part of this, you know, to have these things going on right in Toronto.
Yes, I'm excited about it, and I'm very glad to be a part of Spar, and, as a matter of fact, a part of Canada's space efforts.
Well, thanks for telling us all about what us as Canadians have been up to in the aerospace industry, and keep up the good work. And thanks very much, Chris, for coming by today.
Oh, you're welcome. You're welcome.
Well, it looks like the space shuttle flies, and it does a really good job. This is next week, as we tape this, the next shuttle commander, Joe Engel, will be coming up to Spar to try his hand at the simulator. Our next show will feature an excellent guest, Dr. Helen Hogg. Maybe some of you have heard of Dr. Helen Hogg. She is one of Canada's most noteworthy astronomers, and for 30 years she had a weekly column in the Saturday Toronto Star. She will be with us next month. We'll be talking about the history of astronomy in Toronto. So that's certainly something that you'll want to see. So watch your Rogers listings for that. And of course, after that, we hope to take a trip to the David Dunlap Observatory up in Richmond Hill and get a view of that, and it should be very exciting also. If any of you are interested in learning more about the Royal Astronomical Society of Canada, the Toronto Centre, which has about 700 members, you can write to us, care of the McLaughlin Planetarium at 100 Queen's Park here in Toronto. And if you want to write down that address, we'll be flashing that up in front of your screens on at the ending credits of the show. So I think, as Chris, again, as exciting as the shuttle was and the liftoff, everyone was really relieved to finally see that white shuttle come out of the sky on April 14th and glide down to a safe and successful landing. So as we leave you today, we'll say thank you for watching Astronomy Toronto. We hope that you'll be watching us again in the near future. We'll be coming to you with several shows. And my name is Randy Attwood for the Royal Astronomical Society of Canada. Thank you for watching.
Surely